Morning. Can you hear me? Please confirm. Okay, good. I have some red sign near this sound, but okay. All right, so we'll wait a bit till people are coming. Fix the camera in the meantime. You can ask in the meantime some questions in the lectures. All right, so if there are no questions, no remarks, I'll simply remind the last things before we start, so that those who are still joining don't miss anything which they didn't hear, and those who are here will have some reminder. We are studying the generalized Lyapunov exponent, which we still have quite a lot to study about, and currently the knowledge of this exponent is still well, it needs a lot of details and many things are not known, despite that, as you saw, this is quite a well, very robust property, which for instance gives the growth rate of moments of magnetic field in turbulence, or for that matter in any chaotic flow, in the case of well, when you consider some small fluctuations of magnetic field which are present in a conducting fluid. These small fluctuations, in fact, can also be as small as thermal fluctuations, so it's not something which needs to be kind of introduced by some external source. So they're always present and they would grow, which means that steady state of conducting fluids which have turbulent flow is has large well, significant magnetic field which interacts with the inertial degrees of freedom of the fluid. So we considered as the last application of this concept, we considered the probability density function of size of polymer in a turbulent flow. We proved that this probability density function has the form which is power law. There is, if you consider, so this was the assumption which we made previously in order to get some conclusions. So this time we proved it, and the reasoning boils down to the observation that if you can claim that probability density function of size in the region between the coil size and the full length of the polymer molecule, if it obeys a power law, then the conclusion is that you can actually fix the value of alpha by considering the growth of R with time. So if you consider moments of size with how they depend on time, dependence is very simple. It's the same as you would write for pair of particles or fluid particles. So it's exponential of gamma kt. That's our definition of growth exponent. Gamma of k, the generalized Lyapunov exponent, gives us the exponent of exponential growth of kth moment of the distance. And because these are polymers, we have the correction which is minus t times tau times k. So the moment which is all moments with gamma k, which is larger than k over tau, would diverge in a steady state according to this equality. If you take the limit of length going to infinity, so you kind of remove the upper cutoff, It's barely visible, this color, so I'll switch to another color. So, and moments with smaller order, in contrast, will have convergent values. So we can understand alpha as that special number for which the growth rate of the moment is 0. All right. So this inequality determines the exponential of the growth. And as you can see immediately, it tells us that, so we can, of course, make a picture for that. So gamma of k is a convex function. So what we will learn, and we spoke a bit previously, is that at k minus 3 it is 0. And at k equals 0 it is 0. The slope here is lambda 1. And the slope here, as you will see, is in fact lambda 3. So I will remind you the definitions of Lyapunov exponents quite soon. And if you look at this plot, you determine if lambda 1 is smaller than 1 over tau. That means that this curve lies above this lambda 1, and we find that this curve, because of convexity, it intersects this, well, let me make it a bit more understandable, so something of that sort. And the curve, which is alpha over tau, intersects gamma at a unique point, which is which gives us alpha. So we have, this is alpha over tau. So this is k over tau. And this intersection gives you the value of alpha. And in contrast, if lambda 1 is smaller than 1 over tau, so there's something like that. So if lambda 1 is smaller than 1 over tau, in contrast, you will have that the solution is negative. So for lambda 1 smaller than 1 over tau, alpha is positive, and this is coiled state. And for lambda 1, which is greater than 1 over tau, alpha is negative. So this is stretch state. So this is kind of reminder with a bit more details and graph of what we learned already. So let me see how many people are here. Well, okay. All right. So what this immediately tells us is that if we consider the dependence of gamma of k on the Reynolds number, we will get some non-trivial dependence of this exponent alpha on the Reynolds number. And what that means is that actually we can get simply by changing the Reynolds number and keeping all the rest of the properties the same, which means that you keep Kolmogorov timescale or average energy dissipation per unit volume per unit time. We keep it constant, we change only Reynolds, so the only effect is intermittency, and then this exponent alpha would have a non-trivial dependence on the Reynolds number. So the reason for this is that if you recall the way we wrote, one of the ways we wrote gamma of k was that you can write it as by using cumulative expansion as a series which has, so let me designate this n sigma n. So this is our logarithmic stretching rate. And we designate this logarithmic stretching rate with psi. Well, okay, let me keep the notation. So you have that this is a series n from 1 to infinity, n factorial, k to power L, n factorial, and here you have integral of, let me write it in this way. So you make steady state average of n sigma 0, n sigma n t1, n sigma n tl minus 1 cumulant, and you integrate it over all times, dt1, dt2, dtl minus 1. So this is our representation, which means that gamma of k has a form which is Taylor series, and coefficients of that series are different. So these are integration over time of irreducible correlation functions of this logarithmic stretching rate. And these irreducible structure functions, you can understand them, they are as cumulants. They really capture the intrinsic correlation of the logarithmic stretching rate in time. So whenever T1, T2, or Tn minus 1 is significantly larger than the correlation time, they become decorrelated with n sigma and at 0, and the whole expression turns to 0. So that's by definition, we single out of the correlation function of the process the part which would be non-zero if any of the variables are not correlated. And the result of this is that all times must be within tau correlation vicinity of time equals 0. And this average is taken in a steady state. So today we will learn better what is steady state. In fact, it's quite simple. It's simply major stretching direction, which we'll talk about in a moment. So this is our formula for the gamma of k, which is kind of explicit formula in terms of statistical properties of the turbulent flow. So you look at this and you understand that you have high order moments of the gradients. So the terms of this series seemingly depend on Reynolds number in a power law fashion. And understanding this, you realize that in fact, each term has, so let us make it dimensionless, as it is traditional, as we did previously with lambda 1, and also with the dispersion of this process, which we called mu. So we always, gamma has the dimensions of inverse time, of frequency, and when we multiply it with Kolmogorov timescale, we get a dimensionless quantity, and that quantity must depend on Reynolds number according to some exponential function beta of k, and we don't know very much about this function. This is why I'm telling that this is kind of very open area which is developing recently. So what we know about this function is that, so gamma prime at 0, as you can see readily from this definition, or recalling what we had previously, is lambda 1. So we know that, so from that you can easily see that beta at 0 is this minus 0.04, which is smaller than 0. Then what else we know? We know the dispersion, and dispersion you can find readily that this is proportional to gamma prime of 0, gamma prime, second derivative at 0. And that already, so I remind you that this has the behavior of n sigma n at 0. So let me write it explicitly, the second order cumulant or the second order correlation, irreducible correlation function, which is simply the same as ordinary dispersion. So it's n sigma n at time t minus lambda 1. Lambda 1 is the Lyapunov exponent. It's the average logarithmic growth rate. We talked about it many times already, that it's the average of this process is lambda 1. And this property is observed to behave as Reynolds to power something like 0.3. So this is more or less what we know. we are in fact not completely certain about these laws, but they seem to be compatible with the numerical simulations. So these power laws were not yet measured. We have several points in the dependence on Reynolds number, and so far there was no consistent study of which would demonstrate that there is this power law dependence. And in fact, it might not be possible because we might still be in the range in numerical simulations. We might still be in the range of Reynolds numbers where you cannot actually have this large Reynolds number asymptotic behavior. And that would be, of course, kind of a problem because we would not be able to use this generalized Lyapunov exponent in many applications. So for our application, let me give you, so it's very reasonable that this alpha is a function which decreases. So I would like to give you the physical implications of this dependence so that you see that the connection between some theoretical considerations and actually what you would see in simulations or in experiments which are performed with dilute polymer solutions. So if you consider gamma of k, then it's highly plausible that it would increase with Reynolds numbers here. So when gamma increases, it pushes the solution down, so alpha decreases. This is, of course, what we expect, that if there is larger intermittency, then there are stronger stretchings present in the flow, and that means that this even weak flow will have enough of strong fluctuations of stretching rate that it will produce slowly decaying significant probability of large extensions of the polymer. So growing Reynolds number implies growing intermittency, which in turn implies apparently that gamma of k grows at k greater than 0, which implies that alpha decreases. Now, what does that mean? So that means that if you look, so what does it mean to increase Reynolds number and to keep, so there is trivial dependence, gamma must scale as inverse Kolmogorov time. So when you change parameters of turbulence, of course, if you change Kolmogorov time, there's nothing to talk about. It's already in Kolmogorov theory, you will change the interaction of the flow with the polymers. However, when you put the same amount of energy, but say the fluid has smaller viscosity effectively, or you increase the pumping scale, so Reynolds increases, at the same time the Kolmogorov time scale is fixed, you increase simply the intermittent bursts of velocity gradients. So they stretch polymers more often to large extensions, despite that. So we let us consider the state below the coil stretch transition. So let us assume that lambda 1 is smaller than 1 over tau. This property is only very weakly dependent on the value of Reynolds number, because I remind to you, this is this exponent. So lambda 1 times the Kolmogorov time scale depends on Reynolds by this law, which is really very weakly dependent on Reynolds number. So for all practically available Reynolds numbers, you can assume that lambda 1 is of order of inverse Kolmogorov time. In other words, up to this numerical factor. So you can assume that lambda 1 is something like 0.1 for all Reynolds numbers. So this is what we have from observations and from smallness of this exponent. So if you have, you are below the coil stretch transition. So polymers most of the time are coiled. Only from time to time they encounter large fluctuation. They are in the region where there are anomalously large stretching rates. So they make this excursion to large extensions, and after a while they get shrink, because on average in the end with probability 1 they will coil again. So then if you consider this situation, you start increasing the Reynolds number. You do not change appreciably this lambda 1, so you can assume that you are all the time in the state where the steady state corresponds to a coil, which in the plot of probability density function of extension of the polymer molecule would tell you that you have a peak at coil size, and you have this power law r to power minus alpha minus 1. So this is what you have when you increase Reynolds number. This picture does not change by itself. However, what changes in this picture is not the position of the maximum, but this value of alpha. So in fact, this alpha is a function of the Reynolds number, and we have every reason to assume that it's going to decrease with Reynolds number. So what are we going to see? We're going to see that despite that we are in the below the coil stretch transition, this alpha at certain point, as Reynolds increases, will become much smaller than 1. And at that point, polymer in fact will have a very high probability of being strongly extended. So alpha small means that probability density function of rho, which I remind to you, we defined that rho is logarithm of polymer size divided by the size of the coil, becomes actually uniform distribution, all right? So then you realize that it means that actually polymers with the same probability will have quite large sizes as small sizes, and it already means that polymer is effectively stretched. So this would be pure effect of intermittency of turbulence, which doesn't have anything to do with Kolmogorov theory. It tells you that the stretching happens not because lambda 1 or inverse Kolmogorov time become larger than 1 over tau. It becomes stretched because of intermittency. So intermittent bursts become so probable, you will see them with your, so if you have this snapshot of turbulent flow in space and time, you will find these bursts quite probable, so they will occur so often that in fact polymers will keep stretch state appreciable amount of time of order 1, and that would mean that actually we have effectively stretched polymers. So the understanding of intermittency in this example brings you kind of physical effect where the stretching can occur for completely different reasons than is considered usually, not because the flow is stronger than elasticity, but because the flow has a lot of vortices which are very strong and are able to keep polymer molecules stretched most of the time, or well, appreciable amount of time. All right, are there any, so if there are no, I would be glad to hear some of you. Do you have any questions on this, remarks? Because this is an example of effect due to intermittency. So far, it's completely theoretical in the sense that, well, there is no reason why it would not happen. But we do not have simulations, we don't have numerical experimental measurements. This is all yet to be done. And of course, I encourage that some of you do this. And in fact, well, some of you actually do this if Emmanuel is here. Okay, so, okay. In any case, so this is a physical phenomenon, which I think is quite remarkable and worth your attention. So then, yes.
Itzhak, can I ask you a question?
Yes.
So this effect that you just described occurs at all Reynolds numbers?
Well, this effect occurs because you increase Reynolds number. So you say do numerical simulation, you have some parameters where you have some typical value of Kolmogorov time. So you have this value of certain value of lambda1, which is compatible with this order of magnitude estimate. And you start increasing Reynolds number. So numerically, you can think of it in this way, that you keep the forcing constant, statistics of forcing, you keep it constant. So very usually we use for kind of injecting turbulence, especially in simulations, we can use very simple Gaussian forcing, which is say white noise and time, or you can use boundary conditions, or you can use any other ways of injecting turbulence. So you don't change the way in which you excite turbulence. Numerically, you simply change the viscosity, you decrease it, okay? So in this way, you do not change the amount of energy which you introduce into the flow, because the amount of energy which is introduced into the flow depends only on large-scale turbulence. It depends on this process of fracturing of which we spoke on the first lectures, where you have that you inject some large-scale eddy into the flow by the forcing. It breaks down, it fragments, and it takes energy to smaller scales. And this process of taking energy from large scales does not really know anything about the actual value of viscosity. Viscosity simply, in the end, will absorb all the energy which it gets from large scale eddies. So then you can decrease viscosity in your simulation, which means that you will actually kind of let's assume that you do it in dimensional form. Of course, you can translate what I'm telling into dimensional form. And in fact, you can also do it experimentally. So experimentalists really have the ability of decreasing the viscosity of polymer solutions, well, viscosity of kind of solvent. And they do it to observe different things. So once you do this process, and you need to imagine that you can do it indefinitely, so you can decrease viscosity to be as small as you please. So you will increase the Reynolds number, and this would produce increase of decrease of this alpha. And what you will see actually when you make say histogram of sizes of polymer molecules, you will see that you simply have more and more so in the end, what is kind of the result of simulation? The result of simulation is that you have this histogram, and you will see that it will start rising. So you will not change the amount of energy, but the inertial cascade of energy can proceed to smaller scales. And as a result of this fracturing, so when cascade goes to smaller scales, it is able to produce stronger bursts. Okay, so it has. You need to think about going down the inertial range as kind of there's something that kind of accumulating. So the longer this range is, the higher the burst which you can get in the end can be. This increase of Reynolds number would have nothing to do with the energy you inject into the flow, and yet polymers will know about it. Okay, so this is
I guess I'm not sure if I understand it correctly. So this stretching of the coils is because you mentioned that the stretching of the flow is not really what's driving it. Is the turbulence or the eddies. But is it correct to think that the turbulence itself is locally creating regions where the flow is stretching? Is that a way of thinking about it, or is a completely different phenomena that I'm not grasping?
Well, I think you get it quite fine, really. There's no problem. So let me make a picture, because it would make it also understandable for others, more understandable for others. So more or less what we are talking about. So this gamma of k are due to the events when you have, so what is gamma of k? It simply tells you the rate of separation of pair of particles which are close in turbulent flow, and the rate of separation simply tells you what is the local gradients during some appreciable amount of time, so that they can keep the separation of the pair for some large time at the same, more or less the same rate. So how this happens? The pair of particles occurs in the region where gradient is much larger than its typical value, which is given by average energy dissipation divided by nu, which is the same as 1 over Kolmogorov time. So once the pair gets to this region, it is region of much stronger vortex, and the pair separates much stronger than in nearby region, which is typical turbulence, where the separation will proceed something like that. Okay, so this is grad V of order of 1 over tau k. So this is typical region, which means it has probability close to 1, and this region is atypical rare region of turbulence. However, what intermittency does, it increases the probability of these regions where the gradients are strong. Okay, so you need to be careful. It's not that the intermittency increases simply the regions of strong bursts, because in fact, when you increase Reynolds number, turbulence becomes calmer in larger and larger regions of space and time. However, when you do get to the region of strong burst, the typical value which you would find in that region would be increasing function of Reynolds. So in this way, intermittency doesn't increase simply the occurrence of strong vortices. It in fact decreases the probability of strong vortices. However, once the vortex which you see is strong, it is stronger than its typical strength is growing with Reynolds number, and the net effect is that the separation which you get in these rare regions is so strong that it forms this generalized Lyapunov exponent at all positive k. So it also forms k, which is alpha. So what does it mean in physical terms? It means that when you switch from a pair of particles to a polymer molecule, so you can think of this dumbbell model or simply this elastic spring, it doesn't really matter. So you have that the polymer which occurs in this region is stretched so much that it is, despite that most of the time it will be in regions where there is not much stretching, it will kind of be stretched so much that before it fully relaxes to the coil, it will occur in another strong burst, and then it will kind of have continue to keep large probability of having size which is much larger than the size of the coil. Now, as you can see immediately, the fact that we neglect that the length of the polymer molecule is finite becomes here relevant, because we are considering kind of idealized situation where nothing, where this L goes to infinity. So we are all the time in the region between the coil size and the full length of the polymer molecule. So then, in principle, this strong burst can stretch the polymer molecule to any length which we wish, okay, to any size which we wish. Now, in reality, there will be this limitation from the length, and it will also have an effect. So the reality is indeed more complex, and what needs to be done is simply we need to make measurements and see what is this dependence and how it will be. So I hope that I responded to your question.
That's more clear. Actually, you also answer another question that I have regarding how was the model for the coils, and of course it's not including anything like finite sensibility or anything like that. So that's interesting to, I think it will be interesting to see what's the effect. But yeah, you answered my question. Thank you.
Yes, so you're welcome. And yes?
Can I ask a question? It's actually more of a clarification than a question because you've covered it before.
Okay.
So when you talk about regions of these strong bursts, which grow faster, if I remember correctly, the probability of like the fraction of volume which of these regions is having the strong growth rate is actually exponentially decreasing in time, right? Is
Well, here I believe that you do get a bit confused because the fraction of volume of initial conditions is decreasing exponentially in time. Here we are talking about fraction of volume which is occupied by strong vortices at given moment of time. So it's a bit different. We are talking about how intermittency gets translated into the strong dependence of this gamma on Reynolds number. Okay.
so it's like a time snapshot. You're not trying making evolve in time. Is that it?
Yes. So we are looking. So this picture is kind of taken. So initial position is so it's snapshot of turbulent flow at given moment of time. Let me maybe isolate this picture. So
But when you say steady state, you have to let it evolve in time, right?
yes. So you consider initially at t equals 0, polymer is here, and in most of the flow, you have typical situation where grad V is of order of inverse Kolmogorov time, so you can estimate the gradients from the energy dissipation rate, the mean energy dissipation rate. However, you have these rare regions. And now I'm thinking about this snapshot also as a kind of in terms of its implications for evolution. So out of this vortex, the polymer will be stretched in time. This is so this is time axis already. So it might be a bit confusing. So this is t equals 0. Okay. So then with time here, the polymer will be stretched much stronger than here. Okay. So it's both in space and time, and it's not so simple to depict, of course. So if let's see, I can do it as an illustration, so let me do it. Okay, so you start with so we'll take two-dimensional example, which is of course only for the sake of illustration, because two-dimensional turbulence is not intermittent. So you have X, you have Y. So these ideas of Kolmogorov cascade, in fact, work very nicely in the inverse energy cascade in 2D. So this is why this is kind of only for illustration. So you have at t equals 0, say you have here rare strong vortex. Now, typically it's not spherical, so do not understand this literally. It has some geometrical structure. It might be something like a tube, or we simply don't know what it is. We see it's certainly typically, well, not typically, it's not necessarily spherical. Okay? It's not necessarily something isotropic at all. It has large size, it has often large aspect ratio, and the implications of this always need to be thought about. And then you have typical vortex here. So here you have grad V, which you can estimate as simply average dissipation divided by viscosity. And I remind you that average dissipation by definition is viscosity times grad V squared average. So here you have grad V, which is much larger than this average dissipation divided by nu, and of course we need square root here. Okay, so then this so out of this region, by definition, the polymers will be stretched much more than out of this region. Okay? So the stretching rate associated with this region is much larger. Of course, it will last for finite lifetime of this vortex. And in fact, when we consider all this gamma of k, we speak of average gradient over finite time interval of observation. So say, when we consider exponential growth rate, we speak about certain stretching rate, and we consider the fluctuations. Again, I would like to stress this thing because it might go unnoticed. So we consider this finite time Lyapunov exponent. So when we have, say, lambda t equals some lambda, which is, for instance, larger than lambda 1, okay? So it means that we are in the region of strong vortices which stretch the pair of separating fluid particles much stronger than the average stretching which happens at lambda 1. Now, we don't simply tell that these vortices have typical gradient which is in fact larger than inverse Kolmogorov time. We tell more than that. We tell that we are actually considering history of turbulence. We consider a certain configuration of turbulence such that within time t, which we want to be as large as we please, it actually produced average gradient, which was this lambda. Average in the sense of time average over that finite time interval. So what actual configurations of turbulence in space and time are going to produce given value of lambda at large times is a very open question. Because it's not simply that it's a rare strong vortex, it's apparently a rare strong vortex. Then there was probably some typical region of, well, in the history there was a calm region. Then again, there was some strong vortex. Then again, calm region, and so forth. However, the end result of all these stretchings is that by the time t, which is large, we have that on average in time, the pair was stretched at a logarithmic stretching rate, which is larger than the typical rate. Okay, so there are lots of open questions about structure of turbulence and what forms this gamma of k, which we only barely see at Reynolds numbers which are available in simulations usually. It could be that, in fact, these days we will be able to see more because simulations improved. However, in general, it's very, this gamma of k, it is an object which accumulates lots of information about spatial and temporal structure of turbulent flow. Okay, so, all right, so I was explaining, well, there was some misunderstanding about, okay. So this is different kind of intermittency than the intermittency which we considered previously. However, so previously we considered simply volumes of initial conditions which form this lambda. However, of course, it's very much related. Now, why it's not the same? It's not the same because, in fact, this rare strong vortex is only at t equals 0. So when we speak of volume of initial conditions, we speak of these volumes at time equals 0. Now, in reality, to get large stretching by the time t, you don't need to have precisely t equals 0 that there is rare strong vortex. You need that over the history of this separating pair, you had lots of times strong vortices, not necessarily t equals 0. Okay, so this is the distinction between the way we spoke of intermittency in terms of volumes of initial conditions and the way we're talking of intermittency now, which is more, I want that you think in terms of histories of separations and stretchings and how non-trivial it can be. So the only thing which you know is that on average in time, so kind of finite fraction of time, you had strong vortices in this history of fluid particle which moves in a turbulent flow.
And,
okay.
Just
yes.
And these regions of strong vortices will remain same in time?
No, this is what I'm telling. That okay. So what I'm telling is that strong vortices have finite lifetime. Okay. You want to consider separation with lambda t, which is lambda. It's not that you want, it's what in some sense nature dictates us, that if you want to consider polymers, you need to consider this type of events. So that to consider this type of events, you don't need that there is constant strong vortices during arbitrarily large time t. That would be too demanding, too restrictive, okay?
Okay, I get it now, Yes, okay. Thank you.
Any other questions or remarks? I think it was helpful that everything which we talked about. All right. So, so we had here an example of a phenomenon due to intermittency, and there is a remark which I want to make on this cumulative expansion theorem, which is that we defined this gamma of k with the help of average over initial conditions, which is kind of space averaging. So our way of averaging was kind of to throw a pair of particles, infinitesimally close pair of particles at random in a turbulent flow, measure the separation, and then throw it again, or you can of course throw them at the same time. It's kind of a Gedanken experiment, and you measure the separation in each experiment, and then you average over these pairs of separating particles to fix gamma of k. Now, in this way, as I told you, you can get things which depend on realization of velocity field. So if you say have some, you generated numerically some history of velocity field from time equals to 0 up to some large time t, and you use this data, you pick some position at random initially inside this flow, you put there kind of imaginary pair of particles. In reality, you simply consider characteristics of a fluid particle which originates from this x, and then you find that you can determine the stretching history from this matrix of velocity gradients evaluated on the trajectory. And then from that, you can determine simply by mathematical procedure, as we talked, you can determine R of t as R of 0 exponential of m sigma n, this logarithmic stretching rate, which we discussed already at length. And for determining this logarithmic stretching rate, you don't need, of course, any pair of particles. You need only one trajectory on which you are going to solve, to find sigma, and from that sigma determine this m. So you do this experiment many times from x prime. So you don't do it many times. You simply fix some large number of initial positions, and for these initial positions, you determine fluid particle trajectories. From those fluid particle trajectories, you determine for each initial condition this R, and then you average over all the trajectories. So this gives you property which in fact depends on realization of velocity. So it depends on realization of velocity. Now, what these words mean? These mean that if you generated numerically a different solution of the Navier-Stokes equations, driven by statistically, of course, the same forcing, you would find that the result of the measurement, which you would, the same measurement would give you a different, somewhat different formula, okay? Now, what we are telling that effectively, what you get is that this Rk of t will be given by some constant asymptotically, which is realization dependent, times exponential of gamma of kt, where gamma of k is independent of realization, and there would be some corrections, small realization dependent corrections. So the only let me erase this so that I can write something visible. So there is a realization dependent constant here, and then there are realization dependent corrections. So the only claim is that inside this moment, which you will find unambiguously, once you average over quite a large number of trajectories, you will have a property which is independent of the flow. Now, how do we see this? We see this actually from this representation, because this representation, which originally involves only averaging over space, so these angular brackets stand for this space averaging or averaging over random initial position of pairs. In fact, gamma of k involves also time averaging. So this is already in Cumulance, but originally we had, I remind you, we had integrals from 0 to t of the whole correlation function. So in reality, the average which is involved in these quantities is both over space and time, simply by the nature of considered quantity. So if we consider moments, it's not universal. If we consider this gamma of k, it is universal. It is independent of turbulent flow, of realization of turbulent flow, because it involves both space and time average. And the last remark which I want to make about this is that this is very usual that when you do some numerical simulations, for instance, you want to determine skewness of velocity gradients, which means that you wanted to determine this grad v cube modulus average. So how do you do it? You don't produce lots of ensembles. You don't do ensemble average. You do average of grad v cubed as a function of x and t. You average it. We talked about this, but I want, it's a good place to repeat this and to give you some more, example of this. So you average over the volume of the flow, and you average over time, certain time interval, which must be large enough that, so integral from 0 to t over time. So this is integral over both space and time. So let me introduce here another integral sign. So these type of averages are known to converge. So in the sense that you do this type of average for given realization of the flow, you find some answer. And if you did it for another realization of the flow, you would find the same answer. Okay. So this gives you unambiguous averages, and they involve average over both space and time. And this is the same thing here, because gamma of k involves both averages over space and time, then it is well-defined quantity, where well-defined means realization independent. Are there any questions on this? Okay, I think we should take a break. So if you have any questions, please ask them at this point or write in the chat, and after the break we'll continue.
I have one more question, but it's not related to what you're doing right now.
Okay.
You might have covered it before, but so when you consider the stretching of polymolecules, you have two things. One, it's actually the logarithmic range of rate of stretching, and then you have the contraction, which is due to the elastic forces. So what about the inertia of the particles? Would that be a thing which is actually resisting this flow? Did you actually consider that explicitly, or the effect I don't seem to fully recollect?
Well, we have not yet considered the effect of inertia. It is, I hope that we'll get there. So, okay, we'll get there. So for polymers, these effects of inertia of polymer molecule are not appreciable, because you need to think about this elastic spring inside the flow, which actually glues to the flow. So there is no inertial delay in its going with the flow. It simply is actually frozen inside the flow. Now, if you considered, in contrast, the model of dumbbell, this is where you could in fact get this effects of inertia, but it would be a bit different physics. So for dumbbells, you have spherical particles, and if their mass is appreciable, yes, you would have effects of inertia, and they would have some effect, which, as far as I know, nobody actually studied because it has nothing to do with polymers. However, should you find that there is some interesting effect, there would be, I guess, well, of course, there is no problem to do this simulation numerically of turbulence with really dumbbells of that sort. And maybe it can also be realized experimentally. So if there is some interesting effect, you are welcome to study it. And I think that if you find something, it would be quite relevant. Okay,
just one final clarification.
Yes.
So when you say averaged in space and time, can you comment a bit more on the time part, especially with the correlation? So it is time greater than the correlation or less than the?
Well, you need, usually what you do, you simply plot. So we talked about it indeed, and it's good that we repeat things because that way you hopefully will learn these things. So let me give this example. So you solve Navier-Stokes equations, and ideally you have this function of 4 variables, scalar function, which you determine for any x and any t. Okay, so ideally, of course, you don't determine for any t, but you have some large time interval for which you have it. So then it is a random process in space and time, in the sense that its values at each x and t are not predictable. However, you hope that statistical characteristics of this quantity can be predicted. So then you can start from defining space average. So this is what we designated with S. So we use subscript S. So modulus of grad V cube space average is by definition grad V cube integrated over space and divided by the volume of the domain of the flow. However, that defines usually, if you don't have really very large box, usually we don't, it defines a function which depends on time. So it defines some random stationary process. So psi of t, according to this, is random stationary process. Now this process has some finite correlation time, and then you can average it over time. And when you average over time, by the law of large numbers, the convergence will be over. So if we designate the correlation time with finite correlation time, let's designate it t core to distinguish. So I want to distinguish this, of course, from the correlation time of the logarithmic stretching rate, which is another random stationary process we are working with. So you can then average this psi of t. So average of psi of, and this average of psi of t actually defines the quantity which we call the average of grad V cube. Okay, so the average is something which is already not random, of course. So it is approximately integral from 0 to t dt prime over t capital psi zeta of t prime, where t must be much larger than the correlation time, so that you could claim that this quantity no longer depends on t capital. So in practice, you would consider this average as function of t capital, and you would find that it converges to some plateau, and the value in this plateau is the average. And of course, by definition, this is integral dx over omega, integral from 0 to t dt prime, well, dt over t capital, modulus of grad V cube as a function of x and t. And this is actual procedure which is used in numerical works, not all of them, but many of them, that in order to determine, for instance, the scaling of this quantity with Reynolds number, which is a non-trivial scaling, you generate solution of the Navier-Stokes equations, you average over space, and you average over time, where you simply want this time to be large enough that this quantity is already, this function of time is already kind of a constant. All right?
Yes, I was just asking because I got confused when you're taking gamma of k, you don't, you need to have a time less than the correlation time for that the series has non-zero values.
Okay, so for gamma of k, this will be, okay, let me give you why I'm telling you that gamma of k. So gamma of k, by definition, when you use the cumulative expansion theorem, is defined as limit as time goes to infinity, 1 over t, sum L from 1 up to infinity, k to power L over L factorial. And here you actually have integral from 0 to t of dt1, dt2 up to dtl of n sigma n t1 up to n sigma n tl. And then cumulant, where cumulant is defined with the help of space averaging procedure. So strictly speaking, this type of correlation functions depend on the realization of velocity field, okay? Because what do you have here? You have, so cumulant means that you make some kind of rearrangement of correlation functions. It's simply linear combination of different correlation functions of this random stationary process. So what you get in this way from these correlation functions is something which depends on not only on time differences, it in principle also depends on time. So then you make this integral over all times and you divide it by time. So by definition, in the generalized Lyapunov exponent, in this way, you have also time average, and this is the reason why, similarly to this quantity, you get that this is realization independent. Okay?
Thank you. Yeah, it's more clear now.
All right. Any other questions? I think it was, it's at least to people who work on these things, it's very useful that we have all these discussions because you will know what to do. Any other questions before we go for a break? Okay, 15 minutes break. All right, we continue. Somehow I got to settings where my screen is not completely in the center, but okay, it's okay. All right, so we have talked about gamma of k, and what I want that you certainly remember from all these discussions is that gamma of k is a measure of depends on intermittence of turbulence in both space and time. So it accumulates through this average information on where on that trajectory of fluid particle during large time intervals, how often you had large gradients and how often you had typical gradients. This information is inside this gamma of k, which means that it's quite an interesting property to study. It's a different type of intermittent characteristics of intermittency of turbulence. The usual characterization of intermittency is done with the help of these moments of gradients or dissipation, as we talked about in previous lectures. So usually you want to know the properties, typical properties in space and time of instantaneous quantities. And here we rather consider something which accumulates the information on all stretchings during, in principle, indefinitely large time intervals. All right, so this is about this. If you do not have any questions on this, if you understand the words which I'm telling, then let us, I'll give you another example of relevance of intermittency, and then we go to the major stretching direction and to the spectrum of Lyapunov exponents and its properties. So you see, hopefully, that the quantities which we study are of quite immediate relevance to physics. So stretching of polymers is a phenomenon which is underlying this drop in the pressure which is needed to push the fluid through the pipeline. So it's very implied quantity, not the size distribution by itself, but the understanding of when polymers can have appreciable effect on turbulence and why is certainly practically relevant. So our explanation for this so-called drag reduction phenomenon, when small amounts of polymers inside the flow can have large impact on the pressure which you need to push the fluid. So our understanding is that for starters, polymers, turbulence must be strong enough that it stretches the polymers. If the polymers are most of the time coiled, they have really small impact. It's because they're stretched that they start to be appreciably influencing the turbulent flow. So we will talk about this a bit later. At this point, I want to give you another example of relevance of this intermittency of gamma of k, which is this example of magnetic field. So if we consider magnetic field in the fluid which is conducting, and we can neglect its magnetic diffusivity, or in some sense it means that we consider infinitely conducting fluid, then as we saw, moments of magnetic field actually obey the same, are described by this generalized Lyapunov exponent. So this is another immediate application of this exponent. So the only difference, as we saw, is that instead of thinking of volumes of initial conditions, when we speak of magnetic field, we can actually think about volumes of space at moment of time t, which are occupied by, say, very large magnetic energy and determine the whole energy. So our understanding was that if we take as an example of quantity which is of immediate physical interest, the magnetic energy, then it behaves as exponential gamma 2t, and this is larger than twice lambda 1t. So if we estimated the growth rate with the help of typical growth rate, which is Lyapunov exponent, we would be wrong. And in principle, as time increases, the mistake increases exponentially. So then we had this understanding that we can switch from intermittency in initial conditions to intermittency for final conditions, and then we could tell that if we consider space, magnetic energy would be concentrated. The regions of space which would determine the total magnetic energy are in fact decreasing, their fraction decreases exponentially with time. However, more than that, what we can also tell from what we considered during the last hour, the fact that dimensionless Lyapunov, generalized Lyapunov exponent has power law behavior, power law dependence on the Reynolds number, implies that in fact gamma 2 over twice lambda 1, it's not that it's simply larger than 1, it's going to behave as positive power, which is approximately beta 2. So beta, as you can guess, because it's gamma 2, which is quite large from 0, it's not a small number, so beta must be at least this 0.3 which we had as an estimate for the power law of dispersion. So what it means is that you have what we call in the paper hyperintermittency, that it's not that only the regions where the magnetic energy is concentrated decrease exponentially in time. It is also that these regions are also exponentially small in Reynolds number, in the sense that if you consider the volume of these regions, which we described with the help of large deviation function, then you have similar dependence on Reynolds number, and it means that volume fraction, so fraction of volume containing magnetic energy behaves as exponent, and then you have here minus T over Kolmogorov time times Reynolds to some power delta, where delta is larger than 0. And it's appreciable, it's not a small number. So you conclude that it's not only that at large times you need to resolve regions which are exponentially rare in space, they are also exponentially rare in Reynolds number. So you have kind of this, this is why we call it hyperintermittency, because it's kind of intermittency over intermittency. So here at this point, I want to stress that if we consider the same thing for V, which is not intermittent at all, we would have still that distribution of energy is not trivial, it exponentially decreases in space. We simply would not have this parameter, okay? So we would still need to be very careful in the measurements which we do. However, when the flow is intermittent, it becomes a much more difficult task to perform a proper measurement. And this concerns both numerical measurements and experimental measurements. So if you do, say, processing of astrophysical data, as we talked, it can vary where Reynolds can reach 10 to 15, then you really need to think about where the energy is and what it is and what it does, because in this regime, it's going to be huge, according to this law, in regions which are very rare in space. So it's quite, well, unusual situation where you have, so to say, in the limit, the energy gets concentrated in something which doesn't have any volume. So it's different in this sense from dissipation field. So in turbulence, we are used to the fact that dissipation in the limit of infinite Reynolds numbers gets concentrated on a set which is multifractal and has 0 volume in space. So, however, this is dissipation field. The energy of turbulence is contained in large-scale eddies, and it's all over the place. It's everywhere. V square is a smooth field in the sense that as long as you don't consider any kind of any differences, V is continuous. So here the situation is very different. It's not that dissipation is concentrated on the set in the limit on the set which has 0 volume. It is that the energy itself gets concentrated on the set with 0 volume, which means that extreme care is needed in working with this type of quantities. So if you don't have any questions on this type of impact of intermittency, we will go to the study of major stretching direction. Okay. All right. So when I'm erasing, I'll respond to letter by Ilham. So there is, of course, no problem regarding these issues. And I understand that, so at least some of you do not work in theory at all. And for them, this course is quite difficult. So I would be glad if you could ask some questions despite that it's far from what you are doing, but you kind of need it for numerical work. So your questions would be appreciated. All right, so maybe we will erase this title because we're going to consider a different quantity. So I told you that this vector of orientation in the separating pair of particles has some kind of steady state behavior. So it's called major stretching direction. Now this is another quantity which you need to know to work with this kind of quantities, and let's see how it comes about. So we have a pair of trajectories, and they're infinitesimally close at time equals 0, and then you want to consider how they separate in time, and then there is this vector of distance between them. So this is kind of at the same time. Okay. So you want to know typically how the distance between the particles changes. However, there is also orientation. And this orientation has very non-trivial implications, which we will speak about. So let us see how it behaves. It turns out that in order to understand the behavior of the orientation of the pair, so in principle, you need to solve this equation. dm dt is sigma n minus n and sigma n, and study the properties of this solution. However, it turns out that in order to describe the properties of this solution, you need kind of to study a more general object, which again is happening quite often in physics and mathematics, that to get some properties, you need to consider a larger object. And this object is this deformation tensor, of which we spoke. So I remind you the definitions. We introduce Lagrangian trajectories of the fluid, or trajectories of fluid particles, as trajectories which are determined by the local flow. So these are trajectories which all the time move with the local velocity of the flow, and they are labeled by the initial position. And we introduced the Jacobi matrix, which is a function of initial position of the trajectory. It is dqi_tx dxk. And we saw that if, as an application of this quantity, that if you consider at time equals 0 some infinitesimal ball, so again, we make illustration in 2D, so ball is a circle. Then at time t, it will become an ellipsoid. In 2D, it's an ellipse. And actually, the axis, we derived the equation of this shape, which was given in terms of sum of xi squared. So if the initial radius is epsilon, then we have epsilon squared times exponential of twice rho I as a function of time, I from 1 up to dimensional space. So in our case, it's either d equal 2, as in this illustration, or d equal 3, equals 1. So this is the equation of ellipsoid in d dimensions. And exponents of twice rho I t were determined as eigenvalues of matrix, which is W transpose W, or WW transpose, they were the same. So this matrix had eigenvalues which are exponential of twice rho I. So these are eigenvalues. And we assume that they're arranged. So rho 1 is greater than rho 2, greater than rho 3 in 3 dimensions. So they are ordered. So you see that somehow eigenvalues of this matrix determine quite significant geometrical properties. They determine the dimensions of this ellipsoid. And immediately you see that if you think of a polymer, so you think about this ball as some coil from which you start, that if it is stretched, it's stretched into the direction of this eigenvalue, which corresponds to ρ1, okay? Now, this direction has the name, it's called major stretching direction, and it is unique in the sense that independently of what was the initial configuration of the polymer, if it was really a ball or it was something else, which was kind of, say, deformed ball or ellipse by itself, after some time, it's going to be elongated in the same direction, independently of the initial shape. And this is what we are going to discuss. All right, so what the approach which we are taking is we kind of carefully study this matrix W, and here comes a theorem which is known as Oscillators theorem, which is also known as multiplicative ergodic theorem, and it tells you this, that if you consider, so it's kind of similar to the usual ergodic theorem, but it has some things which need understanding. So this was a Moscow mathematician who proposed this theorem in the 50s. And it tells this, that if you consider limit as time goes to infinity of logarithm of W transpose W divided by twice time, this is, of course, a diagonal matrix. Let me stress the dependence on time and on x. Okay. So this has a limit, and it is given by some matrix M transpose times diagonal matrix lambda 1, lambda 2, lambda 3. So I will give this theorem in three-dimensional case, which is of our main interest, but it's really something which you can formulate in any dimension. And also in two-dimensional case where it is relevant, in fact, where N is orthogonal matrix. So N transpose N is unit matrix. All right, so I would like to lock my dog if you don't mind, because it's popping. So if you have, please think in the meantime if you can have any questions. It's going to be quick. Yeah. Excuse me. So if you have any questions, please ask them. If not, we'll continue. So what is the content of this theorem? It tells you that this matrix W, W transpose W, has eigenvalues which in fact grow exponentially in time. And if you want a picture in three-dimensional case, it means that any volume of the fluid, let's talk about balls, but it doesn't really matter, is going to be transformed into an ellipsoid, which asymptotically has very simple behavior. And this is really remarkable. So asymptotically, you have some ellipsoid, which I will make an effort to draw, which I cannot guarantee that no, it's nonsense. Okay, so I need, okay, I'll do this cigar shape, even though it's, well, it's not really what we have for turbulence, as we talked about a little bit. So, okay, one moment, I'll make some effort. So if it is kind of something of this sort, okay. Okay, something of this sort, okay. So it's an ellipsoid which largest axis behaves as, so if it was originally radius epsilon, this behaves as epsilon to power exponent of lambda 1t. This behaves as epsilon exponent of lambda 2t. And the smallest axis behaves as exponent times epsilon times exponent of lambda 3t, where as we discussed, lambda 1 is greater than 0, lambda 2 is roughly lambda 1 over 4, and lambda 3 is roughly minus 5 lambda 1 over 4, and it's the same lambda 1 as we'll see, as we considered before. So this is for turbulence. This is true in general for any chaotic system. This is only for turbulence. So this is again a result of high universality because it shows to you that if you take a turbulent flow, you have random flow, you consider evolution of infinitesimal volume element in God knows what, and yet in a limit of large times, it's going to behave in a non-random way. Its axes are going to grow exponentially with quite definite Lyapunov exponents, with definite exponents, which do not depend on realization of the flow, on time, so essentially, these are things which are very robust characteristics of the turbulent flow. So how do you understand it? Whenever you have this type of theorem, as in our discussion of lambda 1, it means that there is some ergodic theorem which tells you that this lambda 1 or lambda 2 or lambda 3 are in fact given by the something which looks like time average, and then you can use ergodic theorem to claim independence of initial condition x, and also then independence of realization of velocity field. So how we prove this thing, this is what we're going to talk about starting from now. So if there are no questions on this theorem, then we start. All right, so what do we do for the study? We use singular value decomposition, which means that W is a real matrix. So it's called singular value decomposition for those who do not know these things. And it simply means, so you have it in the paper, which I sent you, in fact, in the appendix of the paper with Lebedev. So this is the most successful language of speaking about these things. So you decompose W into a product of three matrices. One matrix is diagonal, so lambda is diagonal matrix whose entries are exponential of row 1, exponential of row 2, and exponential of row 3. We are considering three-dimensional case, and I'll erase the picture already. So this is lambda, matrix lambda, and both R and T and N are orthogonal matrices. So this is equal to 1. All right. So for starters, this is a decomposition which you can always introduce. This is not completely obvious. However, if you think of it, you understand how it is done. So if you consider matrix W transpose W, which is what we considered before, and what Oscillators theorem wants, then you see that W transpose W. Now, let me maybe stress time dependence. So these are all matrices are functions of time. So W transpose W is N transpose as a function of time, lambda square N. Okay. So this is something which you get immediately from this representation. And in fact, it tells you this. So if you take this matrix W, then you can always introduce for symmetric real matrix W transpose W, you can always introduce representation in terms of diagonal matrix. So N is diagonalizing orthogonal matrix. And in fact, this N is unique unless the eigenvalues are degenerate. So it is unique because we will assume that eigenvalues are not degenerate, which is a true assumption in the case of non-degenerate flows. In fact, in particular it's true for turbulence. And we assume that the eigenvalues are ordered. So this doesn't leave any ambiguity, then N is uniquely defined matrix. And then Oscillators theorem implies that there is finite limit as time goes to infinity of this matrix and T, N of T, which is this N, let's maybe call it N0, or N infinity would be more proper name. So this limit exists. This is the implication of Oscillators theorem. We will actually prove this theorem. So I simply want to show to you what it is that we want to prove in this language of this decomposition. So then for these eigenvalues, the theorem tells you that limit as time goes to infinity, 1 over T rho I of T exists, and it is given by this Laplace exponents. So this is different. Yes?
I do have a question.
Yes, please.
BW. Yeah, so if this matrix, it needs to be symmetric in order to be diagonalizable, right? What does it mean from a physical point of view? What system are we looking at? There might be some restriction, right, imposed by the symmetricity of this function of this matrix.
Well, for W, there's no restriction. So W is any. You can introduce this representation for any, well, for our purposes, real matrix.
Yes, yes, absolutely. I was thinking more what it means from a physical.
Okay. So from the physical viewpoint, it means this, that you need to know the orientation of this ellipsoid in space. So there is so eigenvalues of this matrix tell you the length of the axis of the ellipsoid. However, you also need the eigenvectors, which are inside this matrix N. So N is a matrix whose columns are eigenvectors of this matrix. And these eigenvectors actually point along the directions of corresponding axis of the ellipsoid.
Yeah, yeah, absolutely. But the fact that the matrix is symmetric does have some implication on the physical geometry of the system. So do I need to choose particular domain?
That W transpose W is symmetric?
No, W.
No. Oh, okay.
Sorry,
W,
I think that's confused here.
yes, okay, no problem. W is not a symmetric matrix.
Okay.
So if W was a symmetric matrix, we would not need singular value decomposition. We could immediately use diagonalize it. Okay? So thank you for, yes.
I misunderstood. That's why I was a little bit confused. Sorry.
Thank you. It's not, please ask this because I didn't tell this and I had to tell this. So we need somehow to understand what this matrix of which is actual matrix which transforms infinitesimal neighborhoods of initial point x. So for any r, the position of another trajectory, another point would be, so if this will be q of t and x, this point will be transformed into q of tx plus wr. So w allows you, because r can be anything here, w actually allows you to see the mapping of the fluid flow, which is done by the motion of any infinitesimal neighborhood of this of the point x. So you want to know the behavior, what this matrix W does. So you would want to decompose it as some kind of, maybe it's a rotation and then maybe stretching. So you would want something of that sort. And W, so you would want it to be kind of rotation and stretching, but this decomposition tells you that you can do it as rotation, stretching, but not stretching because it's action of diagonal matrix, and then again rotation. So this is more or less what this decomposition tells you. And the reason why we need it is that there are, so we saw that usual behavior is that this distance grows with exponent lambda 1. However, for some r, for some initial orientations, the distance will not grow at the exponent lambda 1. It will actually decrease exponentially. So we want to be able to track the dependence on orientation, and this will actually give us some information on gamma of k, as we will see, because negative moments of distance are in fact determined by special orientations in space, for which this matrix produces contraction rather than typical stretching. So the matrix W, as it stands, it's a Jacobi matrix. So I remind you the definition. So Wik is derivative of the Lagrangian mapping, and it doesn't need to be symmetric. Typically, it's not symmetric. So we need to think about what to do with it besides the diagonalization procedure, because diagonalization procedure will not work. So for those who know this, it means that right and left eigenvectors of this matrix are not the same, and you need to do some other thing, which is called singular value decomposition. Now, this is not the same as diagonalization of a matrix with the help of one orthogonal matrix, because there are two orthogonal matrices here and they're different. So maybe it's not completely visible. So let me produce something which is a moment. Check if I have another marker here. Let me see. Okay. So W of time t is R of t, lambda of t, n of t. These matrices R and N are orthogonal. However, they are different. So it's not that we diagonalize lambda, we represent it as sequence of some non-trivial operations. So action of W on any R consists of rotation due to this N, then you kind of change aspect ratio of the vector. So you multiply it with matrix lambda, which is diagonal. So in certain in direction which is 1 in this rotated frame, it is stretched. In direction 2, it's also typically stretched, and in direction 3, it's typically shrunk. And after you do this operation, you rotate again, but you don't rotate it back to the, you don't do opposite rotation to what this matrix N does. You do a different rotation. In fact, a completely different rotation. All right. So this is a way in which you can represent any matrix. It's a very useful decomposition. It's called singular value decomposition. And these eigenvalues are called singular eigenvalues because they are not actually eigenvalues of matrix W. So please do not get confused. These rows are eigenvalues, or rather the exponentials of W transpose W. And W by itself has eigenvalues. They can be in fact complex, and these rows are always real. Okay, so please distinguish between eigenvalues of W and eigenvalues of W transpose W. So these are singular, so-called singular eigenvalues of the matrix. All right, excuse me, I need to respond to the phone, 1 moment. Let's make a break for 15 minutes, and then after the break we continue. And we will then continue until 1 a.m. Spanish time. All right, we continue. I apologize to respond. So it's very good that Tiziana asked this question, because these things might be not obvious. You need some experience in matrices, which in fact you do not get from undergraduate courses. So it's useful, and it's very good that we speak about this. So matrix W is a matrix which has, generally speaking, complex eigenvalues. And these eigenvalues are in fact less useful than the eigenvalues of W transpose W, which provide the actual geometric dimensions of this ellipsoid. So the fact is that for any real matrix, which of course applies also to this W, you can introduce this decomposition as sequence of orthogonal rotation, action with diagonal matrix, again rotation. Okay, so this is what we are using here. And if you are not familiar with this fact, I can actually derive it. The derivation is not that long. You can simply construct it. I'll give you some ideas that you need to observe that this type of matrix, in fact, you can take its square root, and then you can actually simply construct this decomposition and demonstrate that it holds. It's useful because it allows you to work with actually symmetric matrices, and not for which things are much simpler. As you know, they have real eigenvalues, and eigenvectors are orthogonal, and right and left eigenvectors are equal. So right and left eigenvectors in this context means eigenvectors of W and of W transpose. So in this case, of matrix and its transpose, which of course for symmetric matrix is simply the same. All right, so this also, I make a remark since you are studying. So this is also true for complex valued matrices, where these matrices R and N must be unitary. So it's very general fact, which we use for real matrices when unitary is orthogonal. So by definition, you simply take W transpose. Maybe I need to do it. So, well, let's keep the name. So you have from the definition that W transpose W is product of, so you take transpose of this matrix, it's N transpose of diagonal matrix is the matrix itself, R transpose times R lambda N, and this is this formula, this is this N transpose lambda square N. And then you also observe that, so matrix N has interpretation as matrix which diagonalizes W transpose W. And of course, you can similarly consider the matrix which is, this I can erase, the matrix which is W transpose. So for this matrix, you'll find that this is R lambda N times N transpose lambda R transpose, which gives you R lambda square R transpose. So R transpose is matrix which diagonalizes W transpose, and matrices W transpose and W transpose W have the same eigenvalues, which are called singular eigenvalues of matrix W. However, the matrices which diagonalize them are different. Are there any questions on this decomposition? So you can look in, well, in fact, in Wikipedia, there is an article on this. So it's something which is simply to learn and to use when you get some matrices which are not symmetric. All right. So, yes.
It's just a very basic question. So W represents the strain tensor, right?
No. W is called deformation tensor, and it's different. So strain, we usually call strain this. So this is not in fact strain, but it's rate of strain. So the name comes from study of elasticity, in fact. So if you consider an elastic medium, then you have the strain. So strain is the word which, as far as I know, belongs to elastic media which do not flow. So say if you take, say, a table and you apply some pressure to it, then it is under strain and you can speak of strain. In fluids, by definition, are media which cannot withstand strain. So for fluids, we speak of rate of strain, which is defined as symmetric component grad I Vk plus grad K Vi over 2. Okay. Hello?
Yes. So it's
Okay.
rate of strain. And so what does
okay.
W transpose
Yes.
W mean?
So W by itself, as you can see, so I remind the equation which we didn't dwell too much on it, but W obeys this equation. So it's it's rather time, so-called time-ordered exponential of this sigma. So if sigma was constant, you would need to exponentiate W. So sigma is somewhat similar to rate of strain. So symmetric component of sigma is rate of strain, but W is matrix which evolves according to this rate of strain. And then what it means is, well, we actually saw already, and we will see more. It simply allows you to see how you transform vectors. It's well, there's not much more than I can tell that that W is simply transformation. So you have any volume around the initial point X, you take some center, so this X, and you transformation of this volume is represented in this way. You transport together as a rigid body this volume to the new point, which is Q of Tx, which is position of X at time t. Then you deform this volume and you actually turn it, if it was a ball, we turn it into an ellipsoid and we rotate it, okay? So this is more or less how the volume is transported if it was symmetric originally, so if it was a ball. Now, if there was originally some asymmetry in the volume, we need a bit more details. So it's not only that you take a ball, you put it in your point, you turn it into ellipsoid and you rotate it. It's also for asymmetric bodies. Initially, you would need also the other matrix R to figure out what happens, okay? Does it?
Yes, yes. I was more interested to what does the eigenvector, I mean, like, so when you diagonalize W transpose W, you get N represents the eigenvector matrix, right? There.
Yes. We will see what it is. So it is wrong to think that. Okay, let me maybe. Okay, let me formulate Oscillators theorem in a bit different way. So I think I can erase this. So you can understand Oscillators theorem as a bit different statement, that there are three orthogonal directions. So R at time such that. So R at time t, essentially by definition of W for infinitesimal separations, this is R modulus at time 0 times W of t and x, which acts on initial orientation n of 0. Okay. So three orthogonal directions mean that if n0, so let me designate them with ni. If n0 is ni, then limit of, in fact, you can keep it in this way. So yes, let's do it. So limit of logarithm of r time t, well, let's divide it by r times 0. So r times 0, it's kind of simply multiplicative factor, so we don't really care about it. So you take this limit, and this gives you lambda r. Okay. So this gives you some more insight into the Oscillators theorem. Now, how you see it, you write.
Refocus the screen because it's not fully clear.
I can, however, I see it well. You are certain, so maybe it's because the color, this marker is a bit thin. Okay, how do I switch to make my screen the main screen? Because I have somehow, for some reason, I have next to mine Maurizio's screen, and I don't really understand why. So apparently, I pushed some buttons at some point, and okay, one moment. Really strange. Okay, so under view, I get some recommendations. I want to get speaker view. It's still the same. I have next to my screen, I have Maurizio Carbone, and I cannot do anything about it. It's not that I mind, but I do need to see the board. Let's see. So light from the window. Oh, okay. So that I can do something about. Okay, I hope this helps. or maybe I'll do the other way around if I'll close the curtains. Please, I'll close the curtains to solve the issue with the light from the window. Please let me know how I can fix so that my screen is kind of the only screen in speaker view. Because, well, it makes it difficult to see the problems which you can have. Okay, light issue is solved. Okay, so please simply tell me if there is some problem because I see my screen not completely. All right, I hope that in the recording it will not be what I see, but it will be actually the board. All right, so you have this kind of object, which thanks to your questions, I realized that you need to think about it. It's not immediate at all. It's simply kind of infinitesimal transformation. So whenever you have any differentiable transformation of any domain, you can introduce this type of matrix and you can talk about its properties. The new thing is that this matrix depends, so it's something which is not usual, is that it's not simply matrix of derivatives. This matrix actually depends on time and it conveys information on evolution of fluid elements. The rest is more or less kind of, so it's simply a matrix of derivatives of some vector function of space or transformation of space. All right, so you have this formulation, and how you see this formulation, I think that again we need to see how it works so that you can use it. Now this is again some property which is studied in many papers. So knowledge of this matrix W is something useful. So you realize that, so you write, instead of logarithm of R of t over R of 0, you can write logarithm of R square of t over R square of 0, and of course divided by 2. And then you write R square using this formula. So you simply look at the formula and you see that this is 1 over 2 logarithm of n w, you'll see the board in a moment, w transpose w n. Okay, is it visible?
No, it's not really.
Okay, because I have, so in my room it's a bit dark after I close the windows, so maybe this is an issue.
Could you use the red pen? Maybe it will be visible in that case.
Yes, I'll do that. The thing is that I see it for some reason quite well. Okay, one moment. Let me. Okay, so what is written here is that. Okay, I do need to erase some things from the board, so let me erase this. Okay, so logarithm of R square of time over R square of 0, according to this equation, and the equations which we couldn't see, is logarithm of n w transpose wn. So to square the vector, you simply multiply it with its transpose and you get this. And then from the Oscillators theorem, you see that all vectors which are eigenvalues, well, which correspond to eigenvectors of this matrix W transpose W will be transformed according to one of these exponents, okay? So, is it understood? Please, somebody tell me if it is, because I see that there are some difficulties. do you still have, is there still a technical issue?
I think we can see pretty well. No.
Okay, good. All right. So there are three special directions in space for which the limits of the logarithmic rate of growth of R will be given by the corresponding lambda I. Now, at the moment you see this equality, the next thing you must ask, because, well, because you learned something, is how come that you told us previously that independently of initial orientation, this type of limit, logarithmic growth rate, is lambda 1. And of course, then you couldn't recall that when I told you this, I told you also that there are some special orientations. It's holds for almost all orientations. So the orientations, if you look in the plane of vectors, which is spanned by n2 and n3. So this is the plane where actually the growth rate is different from lambda 1. Then you see that this plane actually on the sphere has, so you consider intersection of this plane with the unit sphere, and you understand that it gives you something which has zero measure on the sphere or zero area on unit sphere. So directions for which the rate is going to be different from lambda 1, in fact, have they form kind of a curve on the unit sphere. So how do you see that the rest of the dimensions of the directions are going to have the growth, which is actually lambda 1? For that purpose, you need to make the decomposition. So you consider so you study in more detail what is n W transpose Wn, because you have these so you have these eigenvectors, so you can rewrite it. So you decompose n in the usual way. You write the vector as you project it on eigen directions of matrix W transpose W, and you find that this is sum of exponential of twice rho I times ni squared, I from 1 up to 3 in our case, where ni are simply, oh, it's the same notation which I had here. Well, not good, so some of the notations I need to change. So let me call it P. Okay. So these are these three eigenvectors. So eigenvectors, in fact, are often designated with E, with hat, and this is what I will use here. So Ni, by definition, Ni is projection of original orientation N onto the eigenvector Ei. Okay. So these are quantities which are, of course, smaller by absolute value or equal 1. All right, so this is kind of direct decomposition. Now let us study how it behaves. So you see immediately that at large times, because each rho I has this behavior, then at large times, let me write it here. So I don't want to erase this, we will still need this. So for large times, you have that if n1 is not 0, then nw transpose wn is approximately exponential of twice lambda 1t times n1 squared. And here I make an assumption that so-called spectrum of Lyapunov exponent, which by definition means collection of numbers, in our case lambda 1, lambda 2, lambda 3, is not degenerate. So this is true provided that lambda 1 is strictly larger than lambda 2. And the reason is very simple. So at large times, the exponent which has largest value because of exponential growth of the amplitude will simply determine the behavior of this sum. So it's now we get very simple understanding of this claim that independently of initial orientation, for almost all initial orientations, we have that the growth rate is λ1, because of course consequence of this equality is that for those initial orientations n for which n1 is different from 0, the distance between the trajectories will grow with exponent λ1 according to this equality, and we will get and this proves that actually λ1, which we introduced here from the properties of W, coincides with λ1, which we introduced previously by considering the distance between two infinitesimally close trajectories. So I hope that this is understood, that this is the same λ1, and we also have a quantitative statement that for this you need to be away from the plane, or rather the curve on the surface, which corresponds to n1, which is strictly 0. Okay, so this is about this behavior, and it's in fact very useful because you can this decomposition of W and getting into its structure is useful to understand many properties of evolution of vectors, evolution of volumes, and other properties. So I would like at this point to prove Oscillators' theorem in the way which physicists do. It is found in the appendix of a paper on spectra of turbulence and dilute polymer solutions, which you have. I think I sent it. If I didn't, please tell me, and I'll send it then. So how do you actually get some insight into this theorem? So at first look, it looks, when you simply look at it, you kind of cannot understand where it comes from, because it looks highly non-trivial. Then you get immediately some insight after. So it's usually like this: you look at some result, you cannot understand it, and then you start understanding something, and then another something, and gradually things become obvious. So how do you start getting insight into this theorem? It's very usual that you can get some insight by studying one-dimensional case. So in this case, one-dimensional case is very simple. So, okay, I hope that, I'll simply reproduce these equalities when we need them. I cannot keep them on the board all the time. So let us have a look at one-dimensional case. So our starting point in understanding Oscillators' theorem will be this integral, okay, another red color, will be this differential equation, which tells you that W, which is a matrix, obeys matrix differential equation, where the initial condition is that it is unit matrix, which is immediate consequence of definition that dqi at t equals 0x, dxk is simply dxi, dxk. All right, so this is in brackets, explanation for this initial condition. And in fact, in our case, we have another property, which is that determinant of W is conserved in time, it's 1, and this is, of course, incompressibility. So determinant of W is, by definition, and I hope that you studied these things, is the Jacobian of the map from X to Q of Tx. And because of incompressibility, this Jacobian is 1. Now, how you prove it? You can actually prove it from this matrix equation. And it's a simple exercise to show from this equation that time derivative of determinant of W is equal to trace of sigma times determinant of W. And trace of sigma is 0 by the because trace of sigma is nothing but divergence of velocity field. So this is how you actually see from this equation that determinant of W is conserved, is 1, and Jacobian is 1, and this is the consequence of incompressibility, and this is what you must have by incompressibility, that all volumes are conserved. So then you look more at this equation, and you have this idea of considering it in 1D. Now, when you consider it in 1D, of course, it doesn't mean, well, it's not a good limit for considering incompressibility, because the only flow which is one-dimensional and incompressible is a constant in space. So, well, the solution of divergence dx vx equals 0 is vx equals constant. So one-dimensional limit for incompressible flow is not a good limit. So we consider one-dimensional limit not as kind of for application. We consider it in order to get some insight into this type of what kind of behavior we can have from this matrix W. And if you do so in the one-dimensional case, then it becomes very simple. So you know the solution of this equation, it's immediate. So if we have, if it's not a matrix equation, then, well, there's nothing to be done. W equals exponent of integral from 0 to t of sigma of t prime dt prime, and we have returned to our old Ergodic theorem, which tells us that if you consider logarithm of W of t over t, you find that this is, according to this equation, 1 over t integral from 0 to t sigma of t prime dt prime. And then you can use the ordinary Ergodic theorem to claim that in the limit of large times, it must converge to an average of sigma, where the average is with respect to the initial condition, and the theorem holds for all initial conditions, all initial points x, up to possible set of x which has 0 volume. So this is kind of immediate conclusion which you get from studying one-dimensional example. And this example, in fact, is instructive. So it tells you that somehow you need to solve this equation because logarithm of the matrix is more or less integral of sigma. And the integral of sigma is the quantity which we want to get because we can apply Ergodic theorem for studying its properties at large times once we divide this by t. So you see that Oscillators theorem starts to make more sense once you get this example, because if you compare these statements and you apply Oscillators theorem in the case of one dimension, it's simply the same thing, because this whole quantity in 1D, W transpose and W, this is simply W square. So when you take logarithm, you divide it by twice t, it's the same thing as we have here, simply identical. So then the Oscillators theorem is okay. We don't have any problem with Oscillators theorem in 1D. So this is already quite good. And then there was a problem which overcoming took decades, took quite a lot of time. How do you deal with the fact that it's matrix, the sigma and W do not commute? You cannot really solve this equation. So you can express W in terms of sigma, which is so-called time-ordered exponential, which we will not talk about, but you might have heard it if you studied quantum field theory. There is no simple expression for W in the real matrix case when dimension is larger than 1 in terms of sigma. So what do you do about it? So the approach which we proposed and which was successful is to use this singular value decomposition and to pass from equation on W to equation on R, lambda, and N. So let us do it. So at this point, I will erase this So Oscillators theorem, before I erase it, has another name if you encounter it in literature. It's called Multiplicative Ergodic Theorem. And again, this is something which has, it's still on the frontier of science. When you want to generalize it from finite dimensional matrices to infinite dimensional matrices or operators, it becomes completely open area of studies where probably there are some theorems of similar sort, but we need to establish them and to work on them. So let us then see how we can get these properties of Oscillators theorem. And of course, they have direct physical implications because we are simply describing behavior of small volumes of fluid. So it's quite fundamental object to study. So how do we deal with this thing? So we start from, now you can read it in the paper. So I'll simply more or less repeat the considerations which are brought there. This is, in fact, not the language in which the problem was solved originally. So I'm presenting to you already something which is kind of simplified version. All right, so okay, so we start with this equation on W, and we want to get some insight into its behavior. We write that W is R lambda n, where R and are orthogonal matrices, and lambda is matrix which is diagonal in the case of 3 dimensions. It is exponent row 1, 0, 0, exponent row 3. Okay, and we assume that row 1 is greater or equal row 2 is greater or equal row 3. So the good thing about this decomposition is that it is always, it can be introduced. So you don't need to invent anything here. You simply have it for granted. This is singular value decomposition. And I'll think about actually deriving it for you in maybe next lecture, because well, I don't want to spend time on recording how it's done or simply invent how it's so when I was studying these things, it took me some time to understand, and fortunately I remember that. So I realized that you need the proof of this decomposition, and I will provide it. So what do? You introduce this into the equation. So you write that dtr times lambda n plus r, so you take derivative of the product, plus r lambda dtn. This whole thing is sigma times r lambda n. And you want to get independent equations on r lambda and n. Now, I do want that you think about it as kind of generalization of what we did when we studied evolution of distance between two infinitesimally close trajectories of fluid particles. So we decompose the r into the magnitude and orientation. Here, this is generalization of this. So you can think about this n and r as kind of orientation because they do rotations, and lambda as actual magnitude of which conveys you information on actual magnitudes of distances. Okay, so orthogonal matrices, of course, do not change the magnitude of distance of any vector. So you look at this equation, and you want, similarly to how we derived independent. Well, we reduced the equation on R, so we started with equation dr dt equals sigma r, and we passed from that equation to time derivative of logarithm of r, which was our logarithmic stretching rate, which you saw so many times already that maybe you don't want to see it anymore. And then you have this orientation d and dt, sigma n minus n and sigma n. So maybe I do need some notation for this and sigma n because it's really happening so much. So instead of working with one vector, instead you work with one scalar variable and a vector, but this vector has unit magnitude, so the number of degrees of freedom is of course the same. Now here we do kind of similar procedure. We get rid of, we want to concentrate on behavior of lambda. That's our main interest, because lambda conveys to us the actual magnitudes of distances. So to do this, we need to decompose the evolution, and this is our starting point. Now, what do we need to do? Next step is very similar. It's counterpart of the identity which we had. So we had, when we derived from this equation, these two equations, we used the fact that ddt of, because, let me write it in this way, because n squared by definition is 1, then we could claim that that time derivative of n squared is 0, and rewriting this time derivative as twice n dot dn dt, we could tell that derivative of dn dt is in direction of n is 0, and then we could project the equations. So here we do the same. The counterpart of this identity is, maybe I use another color so that you will see. So the counterpart of this identity is that 0 equals ddt of r transpose r. So r transpose r, however r changes in time, it can be very complex, time dependence, and it is complex. When you take its derivative of r transpose r is always derivative of unit matrix, so it is 0. So then you can write it as r transpose dr dt plus ddt of r transpose times r. Okay? So we get this identity, which in this case is a bit different from that case because we have a matrix in the end, not a vector. However, it gives us an idea what to do with this equation. Namely, well, in fact, I see that I don't really need it at this point. So let me, so we'll need it in the moment, but not in the next step. So I will erase this analogy. Now let us, so what we do with this equation is something very similar to projection. So in order to do this type of projection, as we did with n, you need to multiply this equation from the left with matrix which is R transpose, and from the right with matrix which is N transpose. So what do you get in this way? You get, so when you multiply with R transpose, the first term becomes this, lambda N. Now this term, now we multiply it from the right with N, so N transpose, N transpose is 1, so we are left with this. Now, when you multiply this term from the left with R transpose and from the right with N transpose, the only thing which is left is dt lambda. Then, again, you multiply it from the left with right transpose, so R disappears, it becomes unit matrix, and you're left with dtn times N transpose, and this must be equal to R transpose sigma R times lambda, and we will define this as sigma tilde times lambda. So sigma tilde by definition is R transpose sigma R. So it is matrix sigma, which you rotate to the frame, which is, as we discussed, its eigenframe of W transpose. Okay. So then, what is our next step? We realize that here it's time to use this equation. We use it in a bit different way. So here it's a good point to open the paper, because I want to get to the equations before we finish. So the end result, when you so you realize, well, in fact, finally we don't need this thing. No, we do need, but okay, you will see how. So the matrix DTR, so R transpose DTR from this identity which I erased must be anti-symmetric matrix. Okay. So then you can show that, in other words, it can be time derivative of R can be written as R times omega 2, and the same identity for n tells you that dtn can be written as omega 1 n, where necessarily omega 1 and omega 2 are anti-symmetric matrices. Now, this is in fact rotation, okay? So anti-symmetric matrices. Now, why it is rotation? Because matrix R evolves in time, keeping, so to say, its magnitude, where magnitude is defined as R transpose R, it keeps it constant. So the only change which it can undergo in time is rotation. And rotation in a space of matrices corresponds to multiplication with antisymmetric matrix. It's, in fact, you can also understand in this way the usual rotation of vectors. It's also infinitesimal rotation is given by antisymmetric matrix, for those who know this. And the same thing is true for n. Its evolution consists of kind of rotation in the space of matrices, which is multiplication with antisymmetric matrix. Now, you can readily see that this form guarantees that the constraints that R transpose R equals N transpose N equals unit matrix are preserved by evolution. And any other form will not be. So once you define this, you can write down these matrices, and I think that I'll do it already on the next lecture. So I'll leave 1 minute for your questions or remarks on the derivation. So we are going to derive this Oscillators theorem, and then we will have quite a lot of consequences of that. You will have the ability of considering properties such as mixing, growth of magnetic field when there is finite magnetic diffusivity, which is always finite, and there are quite a lot of applications to this matrix, which you will see. Any questions, remarks? All right, we finished for today. Thank you. You can write me email or communicate in any other way. Well, thanks.